The paper extends Lucas' theorem by introducing congruence criteria for computing binomial coefficients modulo A prime. Elementary proofs for these criteria are presented, analogous to the symmetry property of binomial coefficients. Applications include deriving identities and congruences involving sums of binomial coefficients. This work expands on Lucas' theorem, particularly for cases where binomial coefficient computation is complex, such as when the first index is smaller than the prime modulus. Examples demonstrate the significance of these criteria in number theory and mathematics. In this section, the authors present a novel approach to computing binomial coefficients in modulo A prime number, leveraging the symmetry property of Pascal's triangle. They introduce an extended version of Lucas's theorem, which allows for more efficient computation of binomial coefficients. The key insight is that the computation can be reduced to computing values only for kin 0, 1, m, 2, due to the symmetry property. This work focuses on the first n1 rows of Pascal's triangle, working in modulo n, and uses the symmetry property to extend Lucas's theorem. The authors also use this approach to devise new methods for proving identities and congruences involving binomial coefficients. In number theory, Lucas' theorem is a well-established result that deals with binomial coefficients and their properties. A crucial cancellation identity for binomial coefficients is introduced, stating that for integers n, k, and s with 0 is less than or equal to s is less than or equal to k is less than or equal to n, we have $binom n, k, binom k, s, equals binom n, s, binom ns, ks, $. This identity is then utilized to prove Theorem 2.2, which provides a congruence criterion for binomial coefficients modulo A prime number n. Specifically, for any integers k and s with 0 is less than or equal to s is less than or equal to k less than n, we have $binom k, s, equiv. 1, k plus s, binom, n1s, ks, equals 1, k plus s, binom, n1s, n1k, mod n. A direct consequence of this theorem is corollary 2.3, which gives an alternative form of the congruence criterion, involving the binomial coefficient, binom, ni, k, for some integer I such that 1 is less than or equal to I is less than or equal to n and 0 is less than or equal to k is less than or equal to ni. This corollary states that under these conditions, we have $binom, ni, k, equiv. 1, k, binom, I1 plus k, I1, mod n. Furthermore, Theorem 2.4 is presented, which is a variation of Theorem 2.2. This theorem states that for integers k and s with 0 is less than or equal to s is less than or equal to k less than n, we have $binom, k, s, equiv. 1, s, binom, n1k plus s, s, equals 1, s, binom, n1k plus s, n1k, mod n. Collectively, these results extend Lucas' theorem, providing new insights into the properties of binomial coefficients when considered modulo a prime number. Lucas' theorem and its extensions are applied to binomial coefficients in Pascal's triangle, highlighting symmetry and semisymmetry properties. Illustrative examples include parent left big 248,171, parent right big is defined as 182 mod 251, parent left big 235,205, parent right big is defined as 27 mod 251, and parent left big 23011, parent right big is defined as 25 mod 251, demonstrating the calculation of binomial coefficients modulo a prime number. This is essential for understanding the structure of Pascal's triangle. Figures 1 and 2 illustrate the symmetry property, parent left bigma k, parent right big equals, parent left bigma mk, parent right big and the semisymmetry properties, parent left big ks, parent right big is defined as -1, k plus s, parent left bin1's n1k, parent right big and parent left big ks, parent right big is defined as -1, s, parent left bin1k plus ss, parent right big, respectively. These properties are visualized through symmetry lines S0, S1, and S2 in Pascal's triangle. Regions A, B, and C within the triangle are identified, where these properties hold, depending on the relationships between M, K, and N. The research contributes to a deeper understanding of the combinatorial properties of Pascal's triangle, with implications for various fields of mathematics and computer science. The extension of Lucas Theorem 5 focuses on the symmetry and semisymmetry properties of binomial coefficients in modulo n. It proposes a method to simplify binomial coefficients by applying these properties. The approach involves 3 steps. First, applying symmetry if k greater than m minus k. Second, using semisymmetry if m plus k greater than n minus 1. And third, applying semisymmetry again if 2 meters greater than n minus 1 plus k. The method is illustrated with examples, including the computation of parent left big 33/20, parent right big in modulo 37. This extension aims to provide a simpler equivalent form of binomial coefficients in modulo n, leveraging the symmetry and semisymmetry properties effectively. The page presents 2 figures, Figure 3 and Figure 4, which illustrate the symmetry line S0 and semisymmetry lines S1, S2 when n equals 11. These figures are prepared using reference 12. They demonstrate the application of steps outlined in the previous sections to compute modular exponentiation. The modular exponentiation computations are performed using the equations derived from Theorem 2.2 and Theorem 2.4. Specifically, the computation of parent left big 33, parent right big modulo 37 involves applying step 2 and step 3 of the algorithm, resulting in an equivalent value of 32 modulo 37. Another example computes parent left big 87/40, parent right big modulo 101, also involving step 2 and step 3, with an equivalent value of 40 modulo 101. The remainder of the paper focuses on applying Theorem 2.2 and Theorem 2.4 to obtain identities involving binomial coefficients. The identities and congruences presented in sections 3 and 4 are for illustrative purposes only, and the method can be applied to various other cases. The key idea is to use these theorems to rewrite summation identities involving binomial coefficients, thereby proving these identities. This section sets the stage for the subsequent sections, which will delve deeper into the applications of these theorems. The extension of Lucas's theorem is explored, yielding novel identities through the derivation of congruences. The first equality in Theorem 3.1 is established by applying Vandermon's identity and the properties of prime numbers. This leads to a congruence that, when independent of the prime choice, becomes an identity. The second equality is proven by utilizing the first equality and the cancellation identity. Theorem 3.2 is then presented, which leverages an equality from 4 to derive new identities. The proof involves rewriting the equation for a prime and applying theorems 2.1 and 2.2. This process results in a congruence that, when modulated by a prime, becomes an identity. The duality between these identities and the effectiveness of this new method are highlighted. By exploiting the properties of prime numbers and Vandermon's identity, these theorems provide a powerful tool for deriving novel identities. The significance of this approach lies in its ability to generate congruences that can be modulated into identities, offering a new perspective on Lucas's theorem. The development of a novel identity related to congruences is the primary focus of this research. It begins by highlighting the independence of the congruence, 7, from P, leading to an equality. This equality is then used to derive the second equality in the theorem. The identity is closely related to a similar identity in 2. Following this, Theorem 3.3 is introduced, which involves a summation and its relation to S and M. The proof relies on an equality from 4 and manipulations involving prime numbers. The theorem is shown to be independent of P, leading to an equality. The final section presents Theorem 3.4, focusing on another summation and its relation to S. The proof uses an equality from 4 and involves the selection of an odd prime number. The theorem is also shown to be independent of P, resulting in an equality. This extension of Lucas's theorem derives a congruence independent of the prime modulus P. We begin by showing that congruence 11 is equivalent to an equality for sufficiently large P, leveraging Theorem 2.2. Next, we prove Theorem 3.5, which involves a summation identity. This identity is then used to establish congruence. 13, also independent of P. The proof relies on Theorem 2.4 and involves a transformation of the summation. Notably, these congruences bridge seemingly unrelated results, highlighting their significance in number theory. Theorems in number theory, particularly those related to congruences, are discussed. Theorem 4.1 presents a congruence relation involving the summation of reciprocals of integers modulo A', proved using an equality from 2, identity 1.45. This theorem is further utilized to derive another congruence. Theorem 4.2 discusses the case of an odd prime and an integer r, where a specific congruence holds depending on the value of r, relying on an equality from 2, pg. 4.5. Theorem 4.3 showcases how these congruences can be used to prove various results, including the congruence of Fp and Fp plus 1 modulo an odd prime p, which depends on whether p is congruent to plus or minus 1 or plus or minus 2 modulo 5. These theorems and their applications demonstrate the power of using summations and modular arithmetic in number theory. Lucas's theorem is extended by presenting a series of congruences related to the Fibonacci sequence modulo and odd prime pages specifically. An equality involving the Fibonacci number fn plus 1 is established, which leads to the derivation of congruences for fn and fn plus 1 modulo p. This is achieved by leveraging theorems 2.2 and 2.4, and manipulating the summations using the properties of the Fibonacci sequence. Through a series of mathematical derivations, the congruences are obtained, providing insight into the behavior of fn and fn plus 1 modulo p for different values of p. The technical details of these derivations are crucial for understanding the extension of Lucas's theorem in this context. The congruences derived in this work are significant, as they provide a deeper understanding of the Fibonacci sequence modulo and odd prime p. By examining the behavior of fn and fn plus 1 for different values of p, new insights into the properties of the sequence are revealed. The methodology employed in this work is rooted in the application of theorems 2.2 and 2.4, which provide the foundation for the derivations of the congruences. The precise manipulation of the summations and the utilization of the properties of the Fibonacci sequence are critical components of the proof. Ultimately, this extension of Lucas's theorem sheds new light on the Fibonacci sequence modulo and odd prime p, and provides a foundation for further exploration and research in this area. The authors declare no competing financial interests or personal relationships that could have influenced the work reported in this paper. The reference list comprises 16 sources, including books, journal articles, and online resources, that provide background and supporting information for the research. The study leverages a novel methodology integrating machine learning algorithms with traditional statistical models to analyze complex datasets. This hybrid approach enables the detection of subtle patterns and trends, significantly enhancing predictive accuracy and reliability.